The next video is about electrolytic cells. So electrochemical cells produce electrical energy from two spontaneous reactions. What we're going to look at today is electrolytic cells, which have to use electrical energy to produce chemical reactions that are non-spontaneous. So electrolysis is what an electrolytic cell's process is. So electrolysis uses an external power source to a molten ionic compound or solution containing ions to cause a non-spontaneous redox reaction. So recall before we do this that redox reactions that have a negative cell potential are non-spontaneous. Such non-spontaneous reactions need to have an applied electrical potential of sufficient magnitude to make the E value positive, so to make the reaction happen. You don't need salt bridges, you don't need a porous barrier to keep the reactants separate because it's non-spontaneous. So you could put these two things together. In fact, they're together in nature all the time and they don't react. And what our job's going to be is to make them react. And so there's three main types of electrolytic cells. They're all really confusing in some way. So I've chosen the one that I think is the easiest to sort of try to talk through. But there's electrolysis of molten salts. There's no water with inert electrodes. Then there's electrolysis of aqueous salts with inert electrodes. And then there's electrolysis of aqueous salts with reactive electrodes. So what we are going to be looking at is type 1. So we're going to look at an electrolytic cell that has molten salts with no water, and they're going to have inert electrodes. So all molten salts they consist of mobile ions. So for example, if you had molten zinc chloride, all that means is that it's not in an aqueous solution, but you've got this like molten or liquid zinc chloride, which is containing zinc ions floating around in it and chloride ions, but not in a water solution. And so the key thing is that you're just going to have these inert, so they're not part of the reaction. They don't have to be zinc or chloride, but you've got these inert electrodes. So for this example, we've got carbon electrodes, and we're still going to have electrons flowing, but you're going to cause the electrons flow by supplying them. So if we look at this reaction, so we're looking at the reaction between zinc and chloride. You've got zinc, which is a cation, which is going to gain 2 electrons to become zinc solid. And if you look on the data package, the potential of this reduction reaction happening is negative 0.76. The chlorine gas, chlorine is negative, so it can give up 2 electrons. So if you look at the chloride ion forming chloride gas, it would produce the 2 electrons. So this is your oxidation, which is going to provide some electrons for the reduction. But this won't happen spontaneously. We want these electrons to flow. We want these electrons to go to the molten zinc ions to form zinc solid, but it won't happen on its own. So what we do is we provide at least 2.12 volts to the cell, and we would cause it to happen. Now the question is, why would you even want this to happen? Like, why do we care about electrolytic cells? Well, let's say I wanted to produce zinc. And zinc metal is something that I would want to get out of some sort of molten ore that I've mined out of somewhere, and it's not pure zinc. This would be a way of kind of getting that zinc out of this molten core or ore and depositing it onto a cathode or an anode so that I could then sell the zinc later. So the key thing is that we want to look at what's happening. So you still have a cathode and an anode. So the cathode is your reduction. So the product at the cathode is going to be that zinc metal. So you're going to get this zinc coating on your cathode. So the zinc is going to get deposited here. And then your product at your anode is actually just going to be chlorine gas. And so what you're going to see are these bubbles. So on your anode, you see these bubbles which would come up to the surface and break, and you'd have this chlorine gas being produced. The industrial application of the cell is called a down cell. So this is something that is actually used. You still are having electrons flowing from the anode to cathode, but you're forcing that to happen by providing a charge. And the cations are still going to the cathode, the anions are still going to the anode. This is only one of the 3 types of electrolysis, but understanding how this works helps you understand how all of them work. And so I don't feel like we need to go through the details of all of them unless you really want to get into these industrial processes someday. So what we're going to move on to now is just sort of a summary of electrochemical and electrolytic cells. I'm not going to go through this too much. This is just sort of like a study sheet. So it would sort of help you put the two together in sort of a comparison way. But the key thing I want you to realize is that an electrochemical cell is a spontaneous redox reaction. An electrolytic cell is a non-spontaneous redox reaction, so it requires the input of energy to push the reactions to actually happen. But why would you want to do it? Well, an application of an electrolytic reaction are decomposing compounds into elements. So like I was kind of mentioning at the other one, so if you went to a mine, so for example, one of the last ones we do in this note is going to be exactly what we would have seen if we'd gone to Tech Cominco. And feel free to go to Tech Cominco any day and do their tour. You can actually see electrolytic chemical reactions in action in there. But there's also down cells, and then there's electrofining, electroplating, and electrowinning, which I'll go into a little bit more detail in. Whereas applications of electrochemical cells are pretty much batteries, right? It's how to store this energy so that we can then use it in something that we want. All right, so now what we're going to look at is this application of electrolysis. So hopefully you understand that electrolytic cells are non-spontaneous reactions that you have to force happen, and what they can do is deposit an ion as a metal, and that's sort of their purpose. So there's three applications that we'll talk about. The first one being electroplating, which is an electrolytic process in which a metal is reduced or plated out at a cathode. It uses an electric current to reduce a dissolved metal cation, so they form a coherent metal coating on an electrode. So plating. You've heard of this, for example, with a silver spoon. It's not a solid silver spoon. It would be silver plated. Or sometimes they can do this with jewelry, and they can do a silver plating on jewelry so that the whole thing doesn't have to be solid, but you can put this nice coating on the outside. So to do this, the object to be plated is going to be at your cathode. So if we look here, this is an example of coating a ring. So we've got this cathode, which is going to be an iron ring. Okay, and we have this copper anode. And so we're going to have the copper anode actually get oxidized into these copper ions. And then the copper ions are going to get reduced, and they are going to be plated onto this ring. So you would have an iron ring that would be plated with copper, for example. So you can read through all this if you want to, but that's sort of the main meat of it, is that you're trying to get these copper ions to plate as a copper metal onto a cathode. The next process is called electrorefining. It's the process of purifying a metal by electrolysis. So for example, if you have an impure metal at your anode, so this is a slab of impure or pig copper, they call it. I don't know if you can see that over here, but it would be a copper that's containing all these different metals. And I'm like, no, I want pure copper. And so we would do sort of what we were doing above, which is that we would have this be our anode. So we'd have it be oxidized. And the only reason we would do that is to get these copper ions out of the pig and into the solution. And then we would reduce them onto the cathode so that we could get pure copper. So your anode would be impure copper, and your cathode would then be pure copper. So a general overview, the copper on the impure anode would be oxidized. You can see the reaction here. And then the electrolyte solution will now contain lots of copper ions, and then you'd reduce them to form a copper solid, and they'll form on this cathode, which is great. So the result, pure copper. So if you started with a pure copper cathode, you would just load more copper onto it. All right, the last one is exactly Tech Cominco. So like I was saying, feel free to book yourself a tour when all this is over. They take you through a bit of a history of Tech Cominco, and then you actually travel to Tech Cominco and get taken inside with a tech, and you go to their where they manufacture zinc. So this is how the process works. They have an anode and a cathode, and then they have electricity being supplied. So right now all that electricity is coming from the dam, which is the only reason if you went to Tech Cominco and watch their videos, they're like, the only reason we've survived is that we have this electricity from the dam. Otherwise it'd be way too expensive to run. But what they do is they apply a current so that they can make a non-spontaneous reaction occur. And the non-spontaneous reaction that they want to occur is as follows. So your anode is a lead plate, and your cathode is an aluminum plate. The reason they chose aluminum is purely because it's super light. So they, in the old days, had to like lift these plates out to get the zinc off, and so they wanted them to be as light as possible. But what you do is you have an anode and cathode in the same solution. They don't have to be separated because they won't react unless you force them to react, so if you want them to. And so what's going to happen is that your anode's going to be oxidized, and so you are going to be having some lead ions entering into your solution. But your solution, so the bath that this is in, is going to be like from ore. And so what you're going to have is a combination of sulfuric acid, so your eyes burn when you're in the plant, and then there's going to be these zinc ions in there as well. It's a bunch of other stuff. But the idea is that you are going to have electrons supplied so that the zinc is going to be reduced. So you want the zinc ions to be reduced to form a zinc solid. And this is going to plate onto the aluminum cathode. And so the other reaction is that you're going to have the lead solid producing lead ions and 2 electrons. And if you look at the potential for this, it's negative 0.76 for the reduction of zinc. And for the oxidation of lead, it's positive 0.13. So you get an overall cell potential that's negative 0.63 volts. So this is a non-spontaneous reaction. So that's why this is an electrolytic cell, spontaneous. And so we'd have to apply a current to make it happen. But the overall reaction we're looking to happen is to have zinc reduced. Why? Well, it's going to get some electrons from the lead, and you're going to form zinc solid and lead ions. And then this zinc is going to plate on the aluminum cathode. And then what they do, I mean, now what they do is they take them, so they let this all happen, they let the redox reaction occur, and then eventually they have this huge machine that goes along and it picks up all of these plates out of the solution, so all of the cathodes, and then they get put on this conveyor, and then they go to this machine in a different room where there's almost like these giant knife blades that come and they slice the zinc coating off of the aluminum plate, and then the aluminum plate can go back into the baths to get electrowinning to happen again, so to get more plated with the zinc. And then this process happens over and over again. And before they had these big machines do it, they literally had guys who had these aprons on who would have to dip in, grab the top, not into the solution, but they would just grab the top of the plate, they'd heave it out, they'd pull it out, they'd scrape it off with their own knives, and then they'd put it back in. And you kind of got paid by however many of these zinc plates that you could get off, which would have been really hard work. So if someday you're really interested in watching an electrolytic process, like I said, please go to a tech tour. We can go as a class maybe someday if we're ever allowed to see each other again. But yeah, that is the end of Unit 6, and that is the end of Chem 60. So I hope you've enjoyed it. Please let me know if you have any questions or you're concerned about finishing, and I would be more than happy to Zoom call with you or whatever I can to help you out. Good luck.